In this video, I will introduce another type of reaction that occurs in aqueous solution. And this type of reaction is called an oxidation reduction reaction. So let's define these terms and what they mean here. So oxidation is whenever an atom or ion will lose an electron. So we can abbreviate this as losing electrons is oxidation. And we can also say oxidation is losing. So we have two different kind of mnemonic devices that will form here to remember reduction and oxidation. And then its counterpart here, reduction occurs when an ion or atom will gain an electron. So we could say gaining an electron is reduction. We could also say reduction is gaining. So you can see that I have kind of created two little mnemonic devices here. So we can remember Leo Ger. That's one way of remembering losing electrons is oxidation, gaining is reduction. And then over here we have our oil rig, which oxidation is losing, reduction is gaining. So whatever way you want to remember these terms, that's great. And you should also note that one cannot occur without the other. So whenever we see oxidation happening, we have to assume that reduction is also happening. So how do we know if oxidation or reduction occurs? We assign what are called oxidation numbers to the species, the reactants and the products that we're taking a look at. And these oxidation numbers, we have rules for how we assign them. So this first rule here, we should note that elements in their elemental form, so say we have magnesium solid, that's its elemental form. We also have the diatomics that are always gases in their elemental form. So we're going to look at some trends. So the diatomic molecules, they will be gaseous in their elemental form under normal temperature and pressure conditions. And then things like metals, so calcium by itself, these are all in their elemental form. And all of those would have an oxidation number of 0. In rule number 2 here, whenever we have a monoatomic ion, so say we have calcium, but in its ionic state, so calcium aqueous would be a 2+ oxidation number because it's the same as its charge. Magnesium, same thing, 2+ oxidation number. We could even have any ion. We could have anions too. So say we have oxide, O2 negative. So in that case, oxygen would have a -2. Then we have in rule number 3 here, nonmetals, so I just indicated oxygen, they will tend to have a negative oxidation number. So we see here oxygen has a -2. In the rare case, it's in a peroxide, so say H2O2, hydrogen peroxide, for example, is one case when it would have a -1 oxidation number. But for the most part, we're going to see it as a -2, and you probably will not see it as a -1 on an exam. But just note that there are those cases. And then hydrogen here, hydrogen we can say whenever it's bonded to a nonmetal, so H2O, hydrogen's bonded to oxygen. Hydrogen in this case would have a +1 charge. Whenever hydrogen's bonded to a metal, so again, this is less likely, you probably won't see this. So something like sodium hydride here would be a scenario where hydrogen would have a -1 oxidation state, oxidation number. But for our purposes, again, I would try to remember hydrogen is usually +1 when it's in a compound. Then we have fluorine here, which will always have a -1. The other halogens, so anybody else in group 7, chlorine, bromine, iodine, these can have positive oxidation numbers at times. And then when they're in a bimolecular compound here, so we have something like HCl, HBr, CaBr2, for example, they will have that -1 charge. But at times, if we're not told, we might have to solve for the oxidation number, the oxidation state, and it could be positive. especially when they are in oxyanions. So for example, ClO3, the oxidation state of chlorine there would be something like plus a positive number, right? Like a +5, because this is a net negative charge on this polyatomic ion. This contributes -6, so this must be +5 for that chlorine. So we're going to do lots of practice with these and show that the sum of oxidation numbers in a polyatomic ion will be the charge on the ion. So let's look at sample exercise 8 here and see if we can find the oxidation state in the bold-faced element here. So in this case here, that would be the phosphorus. So we see that this is a neutral compound. So I'm going to set the sum of all my oxidation states equal to 0. So 0 because it's neutral, right? So it has no charge. I have 2 phosphorus atoms, so P2, and then I have 5 oxygens. And I know the rule for oxygen is that it's going to be -2, the oxidation state, that is, unless it is in a peroxide. So we get net -10 here from the oxygens, and then to that I'll add 2 phosphorus atoms. And the sum of their oxidation states will be 0. So to simplify this, I'll add 10 to each side, and then I'll see that +10 will equal 2 times my phosphorus atoms. I'll divide by 2 here, and my phosphorus would be a +5 oxidation state. So we can do something similar for sodium hydride here. We'll set that equal to 0. We know sodium and hydrogen here are the elements in this compound. I know that hydrogen will be -1 in that rare case that it's bonded to um, a, uh, a metal. So then since the net of -1 and x here has to equal 0, I know that my sodium would be +1 and hydrogen would have to be that -1. So we're asked to solve for hydrogen here. So I could also note that sodium is in group 1. So when ionized, it would most likely be a +1 ion. So I could solve for hydride that way as well if we don't want to memorize things. Now, this is the elemental form of sulfur. And when we're in the elemental state, we know that will be 0. So that we don't have to solve for. In part D here, I now have a charged species. So that -2 is the sum of all the charges of the 2 chromiums in this dichromate ion, and then 7 oxygens, which we know will be -2, except in a peroxide. So that gives me net -14 plus 2 chromiums equal -2. I'm going to add 14 to both sides. So that means that 2 chromium must equal +12. So if I divide by 2, that means each of these chromiums in this compound have a +6 oxidation state. Then we have here tin bromide, and what's going to happen is we're going to solve for tin. We're going to say 4 times -1 for bromine equals 0. And now I know that tin has to equal +4 because I add +4 to both sides. In my last case here, I'm going to solve for sulfur. I'm going to set everything equal to 0. And I know that the halogens, when they're in 2 elemental molecules like we see here, we're going to say that we solve for sulfur, and then we have 2 chlorides, which are both be -1. So I'm going to add +2 to both sides, and my sulfur's oxidation state here will be +2. So as noted, some of the elements might have multiple oxidation states. Specifically, we see elemental sulfur of 0, and then the +2 oxidation of sulfur down below. So we'll continue with more about displacement reactions and these aqueous reactions in the next video.